All right, so the lab we're going to take a look at today is called Common Anions, and it's called Common Anions because we're going to be studying some anions that are common. So pretty well named. Remember that anions are ions with a negative charge. And so this is the first example of these series of labs that we're going to be doing that are basically called qualitative analysis. And basically what we're trying to answer in this qualitative analysis type of lab is the question of, is something present? So is blank present? Is it there? Is it in your solution? And remember, qualitative is just kind of like a yes, no type of thing. We're not going to say how much is present or how little is present. We're just going to say it's either present or it's not present. So for example, you've got a test tube filled with some liquid, and you want to know the question is, let's just go for example, B minus present. Right, B minus, just some generic thing. Is it there? How could you tell? Well, you could use your knowledge of chemistry, and let's say if you know that if you add A plus with B minus, you get a solid, right? So let's say you know that. So what could you do to the solution? Well, you could add some A plus. And one of two things is going to happen, right? So this or this. So if it is present, then you should form some solid, right? Solid. And if it's not present, then there should be no solid. So if there's not a solid, you know that your B minus isn't there. And if there is a solid, then B minus could be present. But you don't know that for sure, right? Just you see a solid, but you don't know exactly what it is. So maybe it is B minus, or maybe it's something else that's forming a solid. So let's say, or maybe it's C minus if this A plus plus C minus form some kind of solid. So you have to be careful in the way you test whether something is there or not, because not only do you want to see the presence of some kind of solid, but you have to make sure that that test only tests for what you're looking at and that there's not any other kind of interfering ion. So what you'll see in this lab today is that we're going to do a lot of separations of these mixtures. So let's think about what kind of anions we're going to be studying today. So the first one, sulfate, phosphate, sulfide, chloride, bromide, iodide, and nitrate. So that's what we're going to be looking for. You can see there's 1, 2, 3, 4, 5, 6, 7 anions. So we're going to go through this and identify whether each one is present or not present. And so we're going to have a known solution that has all 7 ions, and then we're going to have an unknown, which has any number from 1 to 7 of these ions. And so we're going to kind of compare them to see what's in our unknown. So the first step in this procedure is to start separating things out a bit, right? We've got 7 things in here. There's not going to be one test that just tests for one of these 7 things. There's going to be a lot of interference. So we've got to start separating some things out. So the first thing we're going to do is we're going to take some solution and we're going to add some ammonium hydroxide to this solution. The purpose of this is it's just a base. We're just going to basify the solution. So nothing's really going to happen other than the solution is going to get basic. After this, we're going to add some barium nitrate. And what we're interested in here is just the barium, right? The nitrate will just be a spectator ion for now. So we're just going to take a bit of our solution, do these 2 things to it. Once we do these 2 things to it, once we add this barium, we're going to see a reaction. So if you think back to probably Chem 101, barium and sulfate form an insoluble compound. So they'll form a solid. It's a precipitation reaction. So if we have sulfate in our solution, we'll see a solid. If we don't have sulfate in our solution, we might not see a solid. Another one of these anions that can form a solid with barium is going to be phosphate as well. That's a solid as well. So you can see if we form a solid, we know it's one of these two, but we don't know which one. And then barium with any of these other anions is not going to be no reaction, no solid. Right, so no reaction. So what we're going to see, at least with our known, is that we're going to see a reaction because, again, our known has all of these things in it. So our known will have the sulfate and it will have the phosphate as well. With our unknown, if it forms a solid, it's got one of these two. If it doesn't have either. So as I said, once we add the solution, on one side, we're going to get a solid, and the other side, we're going to stay some liquid, right? So on this side, we're going to take a look at the solid or the precipitate. And then on this side, we're going to take a look at what's in solution. And this is called the supernatant. And it's very easy to separate a solid from a liquid, right? A precipitate from its supernatant. And that's just through decanting, basically just pour without spilling any of the solid over. So as we discussed, the solid's going to be this barium sulfate and or this barium phosphate. And then on the other side will be our remaining 5 anions, still in solution. So let's take a look at how that goes. All right, so let's get started with this analysis. So you can see on the left here, I have my known. So this guy here has all of my anions. And then over here, I have my unknown. This just has some of my anions. So we're going to use the known to figure out what's in our unknown. So step 1 is to take about 1.5 mils of each and put them into a smaller test tube. So we'll go ahead and do that. Cap the known. We're just going to use this pipette, just approximately 1.5 mils. Mil right there. And then about 0.5 mil right there. So 1.5 mils of the known. Go ahead and grab our unknown now. Using a different clean pipette. Transfer approximately 1. And 1/2, a little over. Oh well. Cool. And we'll move these two over elsewhere, and I'll get some tape for the other one. Label these known and unknown. Remove these for later use. All right, next step is we should, it's over here. Next step, we should add some ammonium hydroxide until we're basic to litmus. So basic to litmus, I'm going to use this blue litmus paper, and once it's basic, it's going to, oops, my bad. I'm going to use the red litmus paper, and then once it goes from red to blue, that means we're basic enough. So I got my ammonium hydroxide right here. So go ahead, add a couple drops, test, and then keep going if I need to. Should be more than enough. Give it a little stir. And then use this to test my litmus. Let's add a little bit more. Stir it up. And then test with my litmus paper. Yeah, you can see there it's turning blue. It's basic enough. Do the same thing to the unknown. Stir it up. And test with the litmus paper. Cool. As you can see, litmus paper is turning blue, so they're both basic enough. Then lab manual says to add 3 or 4 more drops extra just to make sure. Probably added enough already, but let's just go do it anyways. Cool. Should be basic enough now. Next, we're going to add the barium nitrate until the precipitation is complete. So I got my barium nitrate here. And I'm going to add dropwise, and we should see a precipitation occur in each one of these. Let's take a look at our known first. And what I'm adding here again is the barium nitrate. So you can see some precipitation forming. We keep adding until we think the precipitation is complete. So we don't see any more precipitate forming. All right, this is probably more than enough, but whatever. Do the same thing with our unknown. Let's see if we get the same result. So you can see no precipitate is forming, indicating there's a difference between these two solutions. All right, so as you can see in the video right now, we've got one of our solutions. We've got a solution with some liquid. It's blue here, it's clear in real life. And then we've got a solid kind of dispersed inside of this liquid, right? It's white in real life. I drew it as black here. So how are we going to separate these two? One of the simplest ways to do it is to centrifuge this. So centrifuge it. So basically what you do is you put it in this instrument that spins it around really fast, and then basically the force of the spinning is going to push down all the stuff. Right? The solid is heavier, more dense, so it goes down to the bottom. So at the end, you have a nice solid kind of stuck on the bottom, as you'll see. And then to get rid of the liquid, all you have to do is basically just pour it out. And so this is called decanting. So decanting is basically pouring with the solid remaining where it is. All right, next up, I'm going to centrifuge to separate my supernatant and my precipitate. So I got my centrifuge right here, as you can see. Go ahead, open it up. And then put my two solutions on opposing sides. That way they balance each other out. And then we'll go ahead and centrifuge for a few minutes. All right, so as you can see, the centrifugation is done. I've gone ahead and let the centrifuge stop. I'll open it up. And then the next thing I'm supposed to do is decant to separate the precipitate and the supernatant. So decanting just means pouring to separate the solid and the liquid. So for my unknown, as we saw before, we had no solid, so you can't really decant if you don't have a solid. So we're going to save this part for part E. So I'm just going to put a new label on it and save it for part E. So we don't have any solid here, so that indicates we don't have the anions that would form this solid. So we'll just save this for later. And for now, we'll just work with the unknown. Or I mean with the known, Let's check out our known. So you can see we've decanted, so we've got all the solid nice and on the bottom. We're going to decant into this test tube that I've labeled as known for part E. So I've got my known and my known for part E. I'm going to separate the solid and liquid by decanting. So I'm just going to slowly pour, being careful not to allow any solid into my part E. Cool. So I got a little bit of liquid left. Let's see if we can get it out. Whatever, good enough. Right, so I separated my supernatant and my precipitate. I'll save this part for part E, and then I'll keep working with this part. Next up, we want to wash our precipitate, right? So we still have some liquid in here, and that's got some other ions in it, so we just want to wash it. So we're just going to add some deionized water. Should be plenty. Give it a good shake. And wash it. What we're trying to do is wash away any ions that have not precipitated out. So then we'll go ahead and re-centrifuge this, and then we'll repeat this procedure one more time. I won't show you repeating the next time, but we're going to repeat this procedure about twice to nicely wash our precipitate. All right, so in this next step, we're going to take a look at this solid here, and we're going to try to answer the question of, is this sulfate or is this phosphate, right? They're both white solids here, so we can't differentiate them currently. So the next thing we're going to do here is we're going to add some nitric acid. And really, we just want the acid here. That's what it's for. So let's take a look at what happens. So when you combine barium sulfate and you add some acid to it, nothing happens. There's no reaction. So the precipitate remains or the solid remains. Now let's take a look at what happens to the phosphate. So if you have barium phosphate and you add some H+ to it, it will actually dissolve back into barium 2+ and HPO4 2-, right? Think about the acid-base chemistry going there. So this dissolves then. So if you have solid remaining, that means your sulfate was there. Right, so let's go ahead and split this up into two. So any solid remaining will be the barium sulfate, right, as a solid. So if you have solid, it is barium sulfate. Your phosphate will then dissolve, but you can't tell whether it's dissolved or not dissolved. It's quite hard to tell. And so we're going to take further tests to check out whether our phosphate is there or not. All right, so off screen, I've washed my known twice. So now I'm left with this precipitate. So again, remember the unknown didn't form a precipitate, so we're not going to deal with any of that. We'll just stick with the unknown now. The next step is to acidify using 6 molar nitric acid. So I've got my nitric acid here, and I'm going to add this to the solution to acidify. Just a little bit more. That should be more than enough. Give it a little stir. And then off screen, I'm going to centrifuge this solution to separate out my precipitate and my supernatant. All right, so again, off screen, I've centrifuged this. You can see I still have some solid remaining, so think about what that tells you. The next step, I'm going to transfer the supernatant into another test tube, and then I'm going to add some stuff to it. So let's go ahead and transfer. Cool, good enough. Got my other solid remaining here. All right, so the next question we might want to ask ourselves is whether our phosphate is present in our solution. So it's dissolved, it's clear, colorless, so you can't see it. So let's check out how we're going to figure this out. So basically what we're going to do here is we're going to add some ammonium molybdate. So ammonium molybdate. And then we're going to heat the thing. And so when you combine these two and heat them, what you'll form is ammonium phosphomolybdate, which has this formula. Right there. And so if you go ahead, Google that, you can take a look at kind of what it structurally looks like. And then you can also see here that it's a yellow color, and it's a yellow precipitate in our case in the solution. So what we'll see here is a yellow precipitate after we heat it. So if you see this yellow precipitate there, your phosphate is in solution. If you don't, then it's not. So let's see. This double line again means a solid precipitate. And again, it should be a yellow solid that'll confirm the presence of the phosphate. All right, next up, I'm going to add some ammonium molybdate to this supernatant. Can't really see that well. About half a milliliter. Cool. And then I'm going to heat this and look for a yellow color. All right, so I got my hot water bath. You can see it's reading a little high, around 65, 66 degrees Celsius. Doesn't matter, close enough. I'm going to go ahead and add my supernatant that I added my ammonium molybdate to. So let's go ahead and toss it in there for a few minutes and see if we see the formation of a yellow precipitate. You can see the yellow color is already starting to form, but let's see if we push a little bit further, will we get the precipitate? going to add a little bit more of the molybdate just to see if that kind of pushes this reaction forward. You can see my solution is getting cloudy. That is indicating the formation of a precipitate. Yeah, it's gone full on cloud now. You can see some precipitate on the edges and stuff. So whatever's causing this yellow precipitate, it's definitely there in our known, as it should be. All right, so at this point, you can see we're kind of done with this tree over here. We've taken care of both the sulfate and the phosphate. So let's follow our flow chart back up. And now we're going to focus on the supernatant from earlier. Remember, we separated out the sulfate and the phosphate. So now let's focus on this supernatant. And specifically for this step, we're going to focus on this sulfide. So what we're going to add to this is some acid. We're going to acidify the solution, and then we're going to add some copper nitrate. And so what this is going to do, if we take a look at this sulfide, if we combine it with a copper 2+ in acidic conditions, we will get out a solid copper sulfide. And this is a solid, and it should be black. And so if we see a solid black material, you know you have copper sulfide as a solid. And then the rest of your stuff will stay in solution. It will not react with the copper. So we have a test for the copper now, or for the sulfide. All right, so we're done with the sulfate and phosphate step. So we're taking a look at our supernatant back from A2. And if you remember, we basified this. So it's currently basic, and you can test with this litmus paper. So if it's acidic, it'll turn this paper red. If not acidic, then it won't. So you see litmus paper here. Take a little bit of my known. You can see it's not changing the color. So we need to add some acid to acidify first. We're going to do that with our 6 molar nitric acid. So I'm going to add 6 molar nitric acid here. I'm going to do this very carefully as we are adding an acid to a basic solution. So this can be quite exothermic. Give this a quick stir. And then check with our litmus paper. Yeah, you see, still not good enough. Give it a stir. Again, check with our litmus paper. Yeah, you see, nice and red now. So this guy's acidic. We're just going to go ahead and repeat with our unknown. Again, adding slowly in the beginning because we are adding an acid to a base that will be exothermic. And it is slightly warm to the touch. Not too bad, though. Check with our litmus paper. Yep, you can see that's acidic enough. All right, now that I got my solutions nice and acidic, the next step is going to be go ahead to add some copper to nitrate to this solution and to precipitate some stuff out. So check out the lab manual for what's going to come out. You can see this copper is a nice blue color. Let's see how this goes. Yep, you see that nice brown black precipitate forming. Think about what that is. I'm going to add enough drops until I think precipitation is complete. It's going to be quite hard to tell. So I'm going to err on the side of too much. All right, that's probably way too much, but whatever. Let's try it now with our unknown. Does our unknown contain this anion as well? And we can see no precipitation. I've added quite a bit there. So our unknown does not. Next up, we're going to go ahead and centrifuge this guy to separate the solids and the liquid. All right, back at it. So you can see I've centrifuged out all that kind of gunk down on the bottom of my known. And then, of course, my unknown did not have any precipitate, so there's no precipitate there. To confirm that everything's precipitated out, I can add some more of the copper nitrate and see if more precipitation forms. So as you can see, no more precipitate is forming. So that means all the stuff that was causing the precipitation is gone. All right, next up, I'm about to take about 1 ml of each of the known and unknown and put them in U test tubes. So take about 1 ml of each of these supernatants. Move these to the side and focus. All right, so we figured out the test for the sulfide. So now we're taking a look at the supernatant over here that has these 4 anions. So we're going to take a look at them one by one. We're going to start off with this iodide. And so let's see how we're going to test for that. We're going to add some iron nitrate and some toluene to this solution. So let's take a look at what each of these components should do. So for the nitrate, if we have 2 iodides plus this Fe3+, if these two react, they're going to undergo a redox reaction where the product's going to be I2 and 2 Fe2+. So if you think about the oxidation state of the iodide here, it's -1. Here it's 0. So going from 0 to -1, we have oxidation. So we're going to oxidize this iodide. Then we're going to go ahead and add some toluene to this compound. So if we take a look at our test tube, we're going to say we have water in here and it's polar. And then we're going to add some toluene. Toluene is a non-polar solvent. So we're going to have another layer here that is the toluene. So this guy is non-polar. So polar and non-polar don't mix, right? You can think of this as kind of water and oil. They don't mix. The toluene is lighter, so it's going to be in the upper layer, or at least less dense. So it's going to be in the upper layer. So let's see how that's going to play out. So if we think about this I-, this has a negative charge. So that's essentially going to be polar here, right? So that's going to stay in the polar layer, right? It's an ion down in the polar layer. It can form those ion dipole interactions. And then when we reduce it to I2. And if you think about I2, it doesn't have a charge or anything, and it's totally symmetrical. It's just 2 iodides attached to each other. And so this is going to be non-polar. And so when we reduce this, when we do this reduction from this I-, this I2, the iodide is going to turn into iodine. So we'll have I2. And then since it's non-polar, it's actually going to go up into the toluene layer, right? Not like likes to go with like. So the I2 will move into the toluene layer. And when this happens, you'll see kind of this purplish, reddish color. It depends on the solvent. And so if you see that, that's an indication that you have the iodide. And so if you think about the other interactions, well, could this Fe2 plus or Fe3 plus oxidize other stuff? And the answer is no. So Fe3 plus is a weak oxidant. So it can oxidize this iodide, but it can't oxidize the bromide, the chloride, or the nitrate. You can think of this in terms of, kind of Chem 101 electronegativity, or if you're at the electrochemistry chapter, you can look at the cell potentials for all of this stuff. So at the end, we should end up with some I2 in the toluene layer, right? And that'll be kind of like this purple, more kind of pink color. So that'll be our positive test for I2. Unfortunately, at this point, what you'll see in the video is some kind of mistakes were made. And so this section of the lab, kind of the wheels fall off a little bit. So if you pay attention, the solutions kind of change a little bit, but the footage is decent. I'll fix it later on, maybe next semester. But for now, we're just going to say it's good enough on these two. All right, next up, we're going to add 5 drops of our iron nitrate and 5 drops of toluene to each one of these solutions. So I got my iron nitrate right here. Add 5 drops of that to each one. And then after that, add my toluene. Then I'll go ahead and agitate both solutions and look for a purple layer in the toluene. The toluene is going to be on top. It's hard to see the layer. I'm going to add some more toluene to both just to make it a little bit more obvious. A little bit more of the iron as well, just in case something's going on. Remember, we have our known, so that should always test positive. So if something's not testing positive, it means we've got a little issue to troubleshoot. Let's check it out. What happens when we agitate this solution? All right, sorry about that, a little bit of troubleshooting there. But you can see in our known, we've got this nice kind of purple layer. Looks kind of more pink to me, but we'll go with purple. And then you can see in our unknown, we don't have that purple layer. Our layer is still nice and clear. So whatever's in this known is not in this unknown. All right, so if we think about what we have right now, we have our iodide in our toluene layer. Basically, what we're going to do here is we're going to pipette this toluene out and then replace it with fresh pipette or fresh toluene. More I2 will move in, and then we're going to repeat that process until all of our I2 is gone. So at the end, we'll have our aqueous layer, and then we'll have a clear toluene layer. So what we're doing here is we're extracting all the I2 out of here. And so once we've extracted all the I2 out of here, we can think about what we have left in solution, right? We got rid of the I-, so we're left with chloride, bromide, and nitrate. So let's take a look at how we're going to test for the next anion. And the next one we're going to focus on is going to be this bromide, So what we're going to do is we're going to have this bromide, and then we're going to combine it with some acid and some potassium permanganate. Permanganate is a common oxidizing agent. If you look at it, it looks pretty cool. You can see I Googled it. It's this nice deep purple color. So it looks pretty cool, and it likes to oxidize stuff. So let's take a look at that. 10 bromides, bunch of acid, H pluses, and then 2 of these permanganates. If we think about the oxidation state of this manganese, you'll get that it's +7. So that's quite a high oxidation state. So it's going to want to go down, gain electrons, and thus reduce something or oxidize something else while getting reduced itself. So it's an oxidizing agent. It will oxidize. And so then the products here are going to be manganese 2+ plus 5 Br2 plus 8 H2O. And then if you think about the oxidation state of this bromide here, it's -1. Here in its diatomic form, it's 0. And so it is undergoing oxidation. And so if we think about what's happening in our test tube, right, we have this aqueous layer, and in this aqueous layer, we're going from the bromide to the bromine. Again, this bromine is going to be nonpolar, so it's going to move into our nonpolar toluene layer. And then what you end up seeing is a brown liquid, right? That the brownness comes from the bromine. So if you see a brown, that means you have bromine. So at the end, we're left with this bromine in toluene. Give it this kind of brownish color there. All right, for the next step, basically what we want to do is we want to extract all the stuff that's causing this pink purple color. We want to get rid of that. So what we're going to do is pipette it out, add some more toluene, mix it up. If it's still purple, pipette it out again, and then just rinse and repeat until we've got a nice clear layer like we do in our unknown. Let's go ahead and pipette out this purple layer. All right, you can see, get rid of this, add some more toluene in here. Agitate it. What you're doing kind of here is an extraction. If you take organic chemistry, you learn about this some more. Still see we still have coloration there, so we're going to want to get rid of it, pipette it out. Get rid of it, add some more toluene. Mix it up again. You can see our color is getting lighter and lighter. Let's go ahead and pipette this out, and hopefully that'll be the last one. Add some more toluene. Agitate. Yeah, you can see you're still not done. Pipette out. Add some more toluene. A bunch more just to get it all out. Toluene's a non-polar solvent, so it doesn't mix with water. See, we're getting closer. Keep going. More toluene. Hopefully we don't have pink this time. Getting closer. Hopefully the last bit of toluene added right here. Probably added way too much there. I see it's still a little pink. We're going to go with clear enough. Just pipette some of this out because I had way too much. Cool. And then let's move on to the next step. If it interferes, we'll just backtrack. All right, so you can see at this point we've got two relatively clear layers of toluene. Next up, we're going to add some nitric acid, about 3 drops to each. And go ahead, stir it up a bit. And then we're going to add some potassium permanganate to this solution. And we should see a brown in the toluene layer if we have a certain ion. So you can see we've got 2 pink aqueous layers right now. And you can see both of our tops of our solutions are nice and brown, indicating the presence of the bromine. Not too shabby. On this upcoming part, some slight errors were made. but the overall result is still pretty decent. So let's take a look. So we've taken care of the bromine in this toluene solution. So in theory, all that's left here is the chloride and the nitrate, right? So we just want to identify whether we have either the chloride or the nitrate. And so what we're going to take a look at here first is this chloride. So to this solution, what we're going to do is we're going to add some silver. Some silver nitrate. So you'll see that in the video. And so a chloride plus a silver ion, I think back to Chem 101, these will form solid silver chloride. And so you'll be able to see that video, and this is a white precipitate. And then with the nitrate, there's no reaction. So this white precipitate's gonna tell you whether the chloride is there or not. We'll have to backtrack to figure out the nitrate. In theory, and I forgot to do this example in the lab, as you'll see, the silver chloride as a solid can be redissolved through the addition of ammonia, because that'll form a complex with this silver. So this will go into some silver ammonia complex, and then your chloride, right? So the precipitate will disappear again. And then we can make this precipitate reappear upon the addition of some acid. So when you add the acid, the acid will reprotonate these amines, and then it won't let it complex it, so you'll form the silver chloride again. So you'll form some NH4 plus and some silver chloride, right? Not balanced, but that's the gist of it. So you can see in the lab video, I didn't do these last two steps, unfortunately. Cool. So we've got our known and our unknown, our toluene layer gone. So we're at the final step. In this step, we should add some silver nitrate. And we should see a precipitation occur. So let's check it out. You can see the white precipitate forming in our known. So that's definitely present there. And then let's check out our unknown. It looks to be the same results. A white precipitate. It only looks pink because the solution is pink. All right, so if we think about where we're at, we've only got one anion left, and that's this nitrate. So let's see how we're going to work on that. If we go back up our flow chart, you can see that in multiple spots, we've actually added nitrates to our solution, right? We added some nitrate right there. And then we added some more kind of further up, right? We added it all the way up here. So we've already contaminated kind of this side of the sample with nitrate. So if we try to test for nitrate here, obviously it's going to turn up positive because we've added nitrate. So what we have to do is go back to the original solution in order to look at the nitrate. So we're going to take a sample of the original solution, and then we're going to work with that. The first thing we want to do is get rid of all these other ions, right? We've already tested for them. We're not worried about them. We just want to get rid of them. That way they're not interfering with our tests. And so to do that, it's pretty simple. We just add some base and some silver sulfate. So silver sulfate, the silver will precipitate out all of these other ions and just leave the nitrate in solution. So in terms of what solids you're going to see all of them, right? Silver chloride, silver bromide, silver iodide, silver phosphate, and silver sulfide, right? You'll see all of them come out of solution, which means the one thing that stayed in our solution will be the nitrate, right? So we're going to centrifuge and then take our supernatant here, our nitrate. To this, we're going to add some iron sulfate and then some sulfuric acid, H2SO4. So let's take a look at what that does. So if we have nitrate, combine it with this iron 2+. You can see your lab manual for the balanced equation. I'm not going to balance this equation just because it's easier not to. So we've added some iron 2+ from the iron sulfate, and we've added some acid from the H2SO4. So what will happen is you'll get some iron 3+, some NO, and some water. And so if we think about what happened to the nitrogen here, you can tell this, oops, forgot a negative charge there. You can tell that the oxidation state here, they should say here is +5, whereas over here it's going to be +2. So +5 to +2, that is undergoing reduction. And in the meantime, you're oxidizing your iron. And so we have this NO here. If we combine this with our original iron, we can form this coordination compound. And this will happen in the acidic conditions. So what this is going to look like, if you have your test tube, we're going to have kind of a layer here. We're going to pour in a layer of H2SO4. Very thick layer. You'll see we're going to pour it slowly so it goes down in the bottom. And then right at this interface, that's where we're going to see our NO. So this is called the brown ring test. And if we see this, then it's positive. If we don't, then it's negative. You'll see in the video, I had a lot of trouble getting a good image of this brown ring on the video, so I just took a picture instead. And then after that, we're all done. We've identified all 7 of our common anions. For the sulfate test, I'm back to my original solutions. Got about 1 ml of each. First thing we're going to want to do is take some sodium hydroxide and basify to litmus. Let's see if that's good. Basic. And basic. Cool. Next thing I'm going to do is add some saturated silver sulfate until the precipitation is complete. So I've got my silver sulfate over here. And I'm going to add that until precipitation is complete. Kind of hard to tell. Just add a little bit. Centrifuge, and then we'll come back to it. Let's try to centrifuge, and then we'll add more and see if more precipitate form. You can see I've gone ahead and centrifuge, got my solid on the bottom. Let's add some more silver sulfate to test if the precipitation is complete. As you can see, we still got more precipitation on this side. Push a little bit there. And some more precipitation probably on this side too. Yeah, there it comes. All right, so as you can tell, I've gone ahead and centrifuged both of these solutions. And now let's add some more of the silver sulfate just to make sure all precipitation is complete. And you can see we have no more precipitate forming, so should be good to go there. Next step is to take half a ml of each supernatant and transfer it to a new test tube. So let's take half a ml of this. Transfer it over there. And then 1/2 ml of this guy over here. Transfer that over there. And now we'll be working with these two. Next step is to acidify to litmus. So I got my sulfuric acid over here. Add a couple drops of this guy. Should be acidified. Check it out. So acidic. And acidic. Next up, we want to add 1/2 milliliter of our saturated iron sulfate here to both solutions. Half a mil there. And 1/2 mil there. And then we want to go ahead and agitate these two and then cool them in an ice bath. All right, so I've had them sitting here for a couple minutes. The next step, I'm going to take them out, hold them at a 45-degree angle, add about 1/2 milliliter of concentrated sulfuric acid, doing it very slowly. What I'm trying to do is basically make 2 layers. Let's see how this goes. Start first with our known. Very slowly add 1/2 ml of sulfuric acid, trying to not get them to mix. Let's see if I don't mess this up. You can see I kind of have 2 layers here. And I just want to give it a couple minutes to react. Leave it over here on the side for a bit. I do the same with the unknown. Again, we kind of have these nice 2 layers. So let's let them sit for a minute and then we'll check them out.